I know so many of you focused learners out there are just constantly bombarded by acronyms. So whether you're an IT student gearing up for exams or just someone who's, deeply curious about how our digital world actually connects securely, this guide is absolutely for you. We're going to strip away all the heavy jargon today and look directly at the foundational rules and devices that make the internet actually function. To keep things simple, we've organized these pretty dense networking concepts into 6 manageable building blocks for our roadmap. We're looking at the rules of the road, the OSI blueprint, hardware checkpoints, TCP versus UDP, the everyday magic of DHCP and DNS, and finally, surfing the web. Starting off with Section 1, the rules of the road, preventing digital chaos. At the heart of it all is a protocol, which is really just a strict set of traffic rules and regulations. Honestly, think of it exactly like driving on a highway, just like stopping at a red light or putting on your seatbelt. If your data packets don't follow these specific protocols, they risk getting dropped, corrupted, or even worse, intercepted by hackers. If a data packet just decides to ignore the rules of the road, it simply will not reach its destination safely. It's that simple. Let's move to Section 2, Blueprint. The OSI model, the 7-layer architecture. To really visualize how data moves across these 7 layers, just take a look at that middle column. As this limitless, continuous stream of data from a user moves down the layers, it physically changes its name through a process called encapsulation. It starts as data or a message at the top application layers. Then, in the transport layer, it gets carved up into a segment. Moving down to the network layer, it's tucked inside a packet or datagram. Down again, it becomes a frame at the data link layer, until finally it's pushed out as raw physical bits. It is quite literally like putting a letter inside an envelope, placing that envelope into a cardboard box, and then loading the whole shebang onto a shipping container. Which brings us to Section 3, hardware checkpoints, the physical infrastructure. As we map the hardware to these layers, you'll notice firewalls and gateways sit right up at the application and transport layers. They act as your main gate to the outside world. Dropping down to the network layer, routers are absolutely critical here. They act as the very foundation the entire internet is built upon, mapping IP addresses from source to destination. Further down at the data link layer, we've got bridges and your device's NIC cards handling physical MAC addresses. And at the very bottom, the physical cables, fiber channels, and Wi-Fi signals are doing the literal heavy lifting of transmitting the data. All right, Section 4, delivery, TCP versus UDP, the core careers. When it comes to actually delivering that data, we generally rely on 2 main heavyweights. TCP is the perfectionist. It's highly reliable and connection-oriented. It takes the time to confirm that every single packet arrives perfectly intact, and if one gets lost, TCP will just resend it. Now, that makes it slower, for sure, but it is totally essential for things like web browsing or downloading files. UDP, on the other hand, is the wild one. It doesn't establish a connection or confirm delivery at all. It just fires off data as fast as humanly possible. Its whole motto is the show must go on, which actually makes it perfect for live video streams and online gaming where speed matters way more than perfection. Let's look at how TCP builds its connection using the famous 3-way handshake. It's essentially 2 computers politely introducing themselves before sharing anything. In step 1, a SYN, or synchronized flag, is sent out to initiate contact on a specific port. Hey, are you open? In step 2, the receiver replies with a SYN-ACK, acknowledging the request and saying, yeah, I received your request, let's talk. And finally, in step 3, an ACK flag is sent back. Thanks, connection established. Only after this rigorous little 3-step dance does TCP actually allow your data to start transferring. But, what happens when things go wrong? Say a connection breaks during a massive file transfer at like 95% completion. How does TCP avoid completely corrupting and throwing away the whole file? Well, through the use of special flags like the push flag, TCP can actually demand the remaining buffered data before allowing a fin or finish flag to terminate the session. It effectively says, whoa, wait, send what you have buffered right now before we break this connection, saving your file from total corruption. Pretty smart, right? Okay, let's zoom out a bit for Section 5, Everyday Magic, DHCP and DNS. First up in our Everyday Magic is DHCP. It automatically assigns IP addresses to devices connecting to a network. Literally, the second you join Wi-Fi, your device broadcasts a request, and the DHCP server offers up an address. Without it, you'd have to manually type in a huge string of numbers for your phone, your laptop, your smart TV, everything. And if DHCP fails, That is exactly why you get those incredibly frustrating connected but no internet errors. Your device is technically on the local network, sure, but without an IP address, it can't actually go anywhere. Now, once you finally have that IP address, your computer is going to use port 53, which you can think of as a designated door on a server to utilize our next massive protocol. And that is DNS, the Domain Name System. It's essentially the internet's phone book, translating human-readable domain names into machine-readable IP addresses in milliseconds. Because computers don't understand names like youtube.com, they only speak in numbers. But here's the scary part. DNS can be hijacked or poisoned by attackers. They can secretly redirect your traffic to fake websites that perfectly mimic the real ones, all to steal your login credentials. Wrapping up with Section 6, Surfing the Web and Rapid-Fire Protocols. When you type a URL into your browser, it traditionally sends an HTTP request over port 80 to grab the HTML files. But here's the catch. HTTP sends absolutely everything in unencrypted plain text, making it highly unsecure. Passwords, personal messages, credit card numbers, anyone who is snooping on the network can read them instantly. And that right there is exactly why modern websites use port 443 for HTTPS. The S stands for secure, and it scrambles your data using TLS or SSL encryption, so any interceptors just see unreadable gibberish. You know you're using it when you see that reassuring little padlock icon in your browser's address bar. But actually, hold on, here is an absolutely critical distinction for anyone studying cybersecurity. That padlock icon, it doesn't mean you aren't on a brilliantly disguised phishing site. A padlock just means your connection to the scammer is securely encrypted. It is such a vital distinction to understand when you're learning how to safely navigate the web. Finally, to round out our application protocols, we have SMTP acting as the internet's literal post office, pushing your outgoing emails, while POP3 and IMAP handle receiving them. Meanwhile, FTP acts as your remote file explorer on ports 20 and 21 to upload and download files. But remember, standard FTP sends everything unencrypted, just like HTTP, making it incredibly vulnerable. Which brings us to our final thought for today. If network protocols are really just traffic rules designed for safety, what happens to our data when hackers learn to perfectly mimic a green light? That question right there is the constant, everyday battle of cybersecurity. And mastering these network foundations, knowing exactly how your data moves from physical bits all the way up to encrypted application messages, is your very first step in learning how to fight back.